Hello everyone, this is the 241 Material Science, Serdar Göktepe speaking. In this video lecture, we will cover the topic plasticity, that is the third subsection of the chapter on mechanical properties of materials. Within the last 3 weeks, we have covered the sections on elasticity and thermoelasticity, and this is going to be the third section on plasticity. In the upcoming section, we will be discussing viscoelasticity for 2 weeks or so. So in chapter 4, you have seen structural imperfections, and especially one-dimensional imperfections called dislocations in metallic materials. And plasticity in metallic materials, that is the primary focus of this video lecture, is based on the motion of these dislocations, in other words, line defects. So in metals, plastic deformations occur through a mechanism called slip. And in this figure that you see here, we have, as you see, an edge dislocation that is visualized as an extra plane of atoms inserted into a perfect crystalline structure. And as you apply shear stress in the horizontal direction towards right, this dislocation moves, edge dislocation moves and creates in unit steps of slip at the edge. So the primary mechanism, as you see in this example, also in the movie that I will show in the next slide, is based on the motion of the dislocation, as you see. So if dislocations cannot move, plastic deformations cannot occur. The plastic deformation doesn't occur. So here's the movie where you have an edge dislocation, where B, denoting the Burgers vector, is perpendicular to the dislocation line. In this case, of course, the dislocation line is perpendicular to the plane. In other words, in the out of plane direction. And when I apply shear, as denoted by these arrows, on the top towards right, at the bottom towards left, this edge dislocation moves, as you see here, towards the right. This is essentially the dynamic version of what we have seen in the previous slide. And you see, in this case, dislocation moves in the direction of the shearing, okay? And that is also in the direction of the Burgers vector. And remember, Burgers vector is defined as the mismatch of the starting point and the end point of a circuit that will draw around the dislocation line by taking the equal steps, equal number of steps in all 4 directions. All right. So let me show it here. For example, here. So if you consider this case, if you take 2 steps, 1 to here and 1 to here and 1 to here and 1 to here, then the dislocation plane is here, and the Burgers vector is the vector that is needed to close a circuit. Sorry. Okay. So let's continue with the next slide, where we will discuss why dislocations are moving easier in metallic materials. First of all, metallic materials are constituted by metallic bonds, and as you know, metallic bonds is a concept that can be conceived as a ion cores embedded into an electron cloud. All right. So since this bonding is non-directional, and since the motion of the dislocations is based on the hopping of atoms from one place to the another one, like stepping towards right or left, it is easier in metallic materials that these atoms can hop by replacing another atom's position in the directions that are close packed. In other words, for atoms, that is easier to move in the directions where the density is higher. When it comes to ceramics that are formed basically by ionic or covalent bonds. Motion is much more difficult because, for example, in the case of covalently bond ceramics, you have a directional bonding, and in order an atom to hop from one position to another one, you need to break down the bond. That is much more difficult compared to the motion of ion cores in an electron cloud in metallically bound materials. In ionically bound ceramics, for example, you have here the picture that you see. When an atom wants to move from one position to another one, in other words, hop a single step, for example, this positively charged ion wants to replace the negatively charged ion, that is going to be also very difficult because in this case, you will be bringing equally charged ions close to each other, and that is an extremely uh, difficult process because energetically not favorable. So because, as you know, uh, repulsive forces can develop very quickly, and energetic state will require high energy input to the system. Therefore, this kind of mechanism is not favorable in ionically bound materials. So therefore, we observe motion of the dislocations, defects in metallically bound materials, in reverse metals, much more often. So if you recall from chapter 4 on structural imperfections, we have two kinds of dislocations. One is called the edge dislocation, while the other one is called the screw dislocation, as you know. So in the case of edge dislocation, when it is subject to the shear, the motion is pretty similar, is actually the same as what we have seen in the previous movie. So dislocation moves along the slip plane in a slip direction, and that is perpendicular to the dislocation line. Okay, so in this case, dislocation line in the edge dislocation is in the out of plane direction, and a dislocation moves in the direction of the motion. Uh, Slip direction is the same as the Berger's direction. In the case of edge dislocation, remember Berger's vector has the direction. It has the direction of the motion, essentially. In this case, in the horizontal direction. In the case of screw dislocation, Berger's vector is again in the horizontal direction, in the direction of the shearing, but the dislocation here moves towards the plane, in plane direction. Okay, so these are the mechanisms how the edge and the screw dislocations essentially move. But at the end of the day, when you look at the final configuration of these two defected materials, if you wish, you see the pictures are the same. So without knowing the initial state of the crystalline structure with the defect, by looking at the final state, you cannot judge whether it has a screw dislocation or edge dislocation, resulting in such a stepping on the surface. Another picture here shows how these mechanisms, dislocation motion actually evolves. In this case, again, you have shearing and dislocation moves in that direction, and that is also the direction of the slip. But here, in the case of screw dislocation, dislocation moves in this direction, but the slip is in the horizontal direction. Remember, slip direction coincides with the direction of the Berger's vector. In this case, Berger's vector in the edge dislocation is in this direction, and the same also here, as it is nicely presented in this figure that is borrowed from the book by Callister and Redwich. So in this case, we have a three-dimensional crystalline material where we have a combined edge and screw dislocations. Here on this side, we have the screw dislocation where the dislocation line is, as you see, in this direction. Here, on the other hand, we have an edge dislocation. So this is like combined dislocation. And when you look at this crystalline sample from the top, where this point A corresponds to point A here, and point C here is here. So you see this curved line denotes the dislocation front. As you deform this material, edge dislocation moves in this direction, in other words, in this direction, while the screw dislocation moves in this direction, but at the end of the day, you see the slip will be in this direction as the front propagates. Okay, this is a nice picture where the Burgers vector for the screw dislocation and edge dislocation, edge dislocation and screw dislocation nicely shown, depicted. And also the combined form of the dislocation where we have edge dislocation and screw dislocation with the dislocation front here. As you see, as already been probably discussed in chapter 4, um, imperfection is in the neighborhood of the dislocation line, while the region where the dislocation has already moved is perfectly crystalline. We don't observe any mismatch here, and also the region, the domain of the material where the dislocation line yet to pass is again perfect. So you see the dislocation front is actually the region where we have the mismatch of the positions of the atoms with the perfect structure of the crystal. So how does it work? We have said that the dislocations move in the slip on the slip planes in the slip directions, and generally these are the planes in the directions that are densest in the crystalline unit cell, crystal unit cell. If a material is subjected to load, for example, if you take a specimen of this shape and subject it to macroscopically in the testing machine in this direction, you essentially like to activate a slip on the slip plane that is denoted by x prime. All right. So in the two-dimensional representation, slip plane is denoted by this line, and slip direction is actually one of the directions, either in this direction, in this direction. So what you need to do is to check whether the external applied uniaxial stress can generate plastic flow. You need to decompose the stress into its component in the slip direction and component in the normal direction. Obviously, uh, slip is based on the shearing, and therefore the most important component that governs the plastic deformation is the shear component that is denoted by PS. So permanent displacement of atoms and molecules from their original motion will generate the permanent deformation and the or plastic deformation. And in general, this process is continuous and deformation is continuously increasing. Therefore, the phenomenon is referred to as a plastic flow in the literature. So let's precisely define what the slip system is. So slip system is composed of a slip plane or groups of slip plane and the slip directions. So a slip plane is the plane on which the slippage occurs easiest. And then generally, hopping is the main mechanism, as we have seen in the motion of the dislocations. Therefore, the highest planar densities, the planes with the higher planar densities, are the slip planes. So that is also related with the large interplanar spacing. And slip directions are the directions of the motion where the linear densities are highest. All right. Okay, so for example, here you see the face-centered cubic crystal. The slip occurs in 111 family planes, which are close packed, and 110 directions. These are also the directions that are densest close packed. So in total, we have here 12 slip systems in FCC, in BCC, and in HCP. We have other slip systems. So if you like to take a closer look at the slip lines in FCC, this is our 111 plane. That is equivalent to the -1, -1, -1 plane. This is -111 plane. Its equivalent plane is denoted here. This is 1 -1 1 equivalent with this equivalent, and this is 1 1 -1 as you see here with this equilibrium. So in FCC, we have 4 slip lines, all right? And for each slip line, we have 3 directions of the slip. For example, if you consider 1, plane, yeah, you can have here the slip in this direction or this direction or this direction. So 4 times 3 makes essentially 12 slip systems for FCC metals. So just to wrap up, slip phenomenon is used to explain plastic behavior of metallic materials, plastic deformation metallic materials, and slip occurs along certain crystal planes and directions that are the directions and the planes that are densest in terms of planar densities and directional densities, because the denser the planes and directions, the easier it becomes for atoms to hold, therefore for dislocations to move. And slip planes and slip directions constitute slip systems. For an FCC structure, as we have seen, there are 12 slip systems. For BCC structure, we have again 12 slip systems. For hexagonal one, we have 3 slip systems. Of course, you can deduce from these numbers that the higher the number of slip systems, the easier for metals to undergo plastic deformation. So that is probably the first thing you should consider. But although FCC and BCC metals have the same number of slip systems, FCC metals, for example, copper, gold, silver, lead, aluminum, they're usually soft and ductile. They can be bent and shaped easily. BCCs with the same number of slip systems, for example, iron or chromium, are less ductile compared to the FCCs, but stronger because they are not as closely packed as FCC. So for that reason, although they have the same number of slip systems, BCCs with the less closely packed structure would behave in a less ductile way, or we observe stronger behavior. HCP metals with HCP structure, for example, zinc or zirconium or magnesium, with a very limited number of slip systems, are generally very brittle. They have fewer slip systems, therefore plastic deformation, that probability that the dislocations move under the action of external applied load will be less. Therefore, this results in a stronger behavior and actually brittle behavior, which is not desired. So how are we going to decide whether the slip will occur or not? So for that purpose, we introduce the concept of resolved shear stress. So assume that you have a cylindrical specimen like this, okay? And when you look at the microstructure of this cylindrical specimen, you observe that you have a slip system, and in the slip system, you have a slip plane that is denoted by this inclined plane, and the slip direction that is denoted by this red arrow. So the result, the angle between the external applied normal stress in the longitudinal direction of the specimen and the normal to the slip plane is denoted by angle phi. So angle phi is defined as the angle between the normal to the slip plane and the applied normal stress direction. There is one more angle that is needed to be introduced, is the angle between the applied normal stress direction, in this case the longitudinal direction of the specimen, and the slip direction, and that angle is denoted by lambda. So lambda is the angle between the slip direction and, or simply the direction of the slip and the stress direction. All right. So now, in order to judge or determine whether slip will occur or not, we need to project this stress or force, if you wish, that is externally applied to the specimen onto the slip plane in the slip direction. Okay, that is a geometrical operation. I have actually two slides explaining this. Let's first take a look at the one that we borrowed from the book by Callister. So assume that this is your cylindrical specimen with the slipped configuration, and this is the externally applied longitudinal force generating a normal stress in the on this face, nominal cross section of your specimen, and this applied tensile stress is computed as you know, force divided by this cross sectional area, that is the area perpendicular to the force, or area whose normal is parallel to the force. Okay, then what you need to do is you need to find the component of the force that is acting parallel to the slip direction, and then divide this force by the inclined surface area of this cross section. In other words, result shear stress is defined as the shear component of the force that is externally applied. In other words, this force divided by the inclined area of the slip line. Okay, that is denoted by, in this case, A sub S. S is standing for shear or slip. So then you can substitute for Fs, F times cosine lambda, because remember lambda is the angle between the force, externally applied force direction and the slip direction. So you gotta project this force onto the slip direction through the cosine lambda operation. And the same way, you gotta calculate the inclined area of the slip plane by dividing the cross-sectional area, gross nominal cross-sectional area of the specimen by the cosine of the angle between the direction of the loading and the normal direction of the slip line. That is the angle phi. So AS is given by A over cosine phi. Fs is given by F times cosine lambda. So when you substitute this, obviously F over A is your sigma, and then cosine lambda and the cosine phi that appears in the denominator will actually move to the numerator and leads to cosine phi factor here. All right, so this is what we call the result shear stress, and magnitude of the stress will determine whether the slip will occur or not, because we have also critical result shear stress, which is sometimes referred to as Schmidt stress in the crystal plasticity literature, and we compare this stress value with that stress. If that is kind of threshold, if the result shear stress is equal to if the result shear stress magnitude of the result shear stress is equal to the Schmidt stress, that is, if you wish, the strength of that slip line in that particular slip direction, then plastic flow will occur. In other words, slip will be initiated. Another remark regarding the terminology, in some books you will see that the cosine lambda times cosine phi, this product is also referred to as Schmidt factor. Okay, so the same thing is explained here. Again, shear force acting along the slip direction can be calculated by taking or projecting the force into the slip direction, that you do by multiplying the force with the cosine of this lambda, cosine of the angle lambda, which is the angle between the direction of the force and the slip direction. And the area of this inclined plane, of course, must be greater than the cross-sectional area we have here. That is the cross-sectional area, is given by A over cosine phi, where phi is the angle between the direction of the loading and normal to the slip line. That is denoted by AS. AS is the area of the slip line. Then the result shear stress is obtained by dividing the projected shear force by cross-sectional area area of the slip plane AS. So if you carry out this operation, you find essentially the same result, where sigma over A is externally measured stress, and the cosine lambda and cosine phi are the direction cosines that are related with the orientation of the slip system with respect to the externally applied force. All right, so if one of these angles is equal to pi over 2, you observe that this results in 0. Therefore, if the slip plane makes an angle which is perpendicular to the direction of the loading, or if the slip direction is perpendicular to the direction of the loading, then it is impossible for us to activate this slip system externally. Okay. So one very nice picture that is obtained from an uniaxial deformation of a cylindrical specimen of zinc, which is a single crystal material. As you see, although you take a perfect cylindrical specimen in the beginning and subject it to uniaxial deformation, the deformed shape is dictated by the microstructure of the material, because when you pull it, essentially dislocations move and the slips occur in the directions and on the planes dictated by the microstructure of the crystalline structure of the material. Therefore, at the end of the day, you obtain such a nice picture where you have a stair-like pattern on the surface. So although you try to deform material plastically by pulling it in the uniaxial direction, material actually deforms plastically as the way that the microstructure dictates. Let's take a look at an example problem. In this case, what you have is a similar picture. You have a cylindrical specimen that is subjected to uniaxial stress, whose value is 45 megapascals. And in this case, a slip plane normal makes an angle 60 degrees with the direction of the loading, and the slip direction makes an angle 35 degrees with the direction of the loading. In other words, phi is equal to 60 degrees and lambda is equal to 35 degrees, consistent with the definitions we had in the preceding slides. So the question is, if the critical resolved shear stress is given to be 22.7 megapascals, will this single crystal yield? Of course, what we need to do is we need to calculate the resolved shear stress by substituting 45 megapascals in the place of externally applied normal stress, and the cosine lambda for lambda 35 degrees and 60 degrees for phi, and calculate the result that yields 18.5 megapascals, which is smaller than the critical resolved shear stress. That is, if you wish, the yield stress or yield strength of the slip system we have here. Therefore, since 18.5 megapascals is smaller than the critical resolved stress, which is equal to 20.7 megapascals, this normal stress will not be able to generate the slip or activate the plastic flow in the material. So if not, what is the stress needed? What is the value of the stress? Okay, so in this case, we do the calculations for a different critical resolved shear stress that is given to be 30 megapascals. What is the stress that is necessary to generate the plastic flow, which can be considered as macroscopically deformed yield stress denoted by sigma y, that we will come at the end of these slides by looking at the uniaxial stress strain curve of a ductile metal. But the yield stress can be defined at this point as the point where the uniaxial stress, in the uniaxial, for example, stress, uniaxial loading, tensile loading, for example, is the threshold value of the stress beyond which the plastic deformations gonna start to evolve. Below this threshold value yield stress, on the other hand, metallic materials, or this can also be defined for glass polymers, polymers behave elastically. So this is kind of a threshold value, below which materials behave pretty much elastically, but the beyond which we start to observe plastic deformations start to or begin to evolve. So let's come back to the question. So the next part is, if not, what is the stress needed to initiate the plastic flow? In this case, I use a different critical resolve shear stress value, which is 30 megapascals, and this now appears on the left-hand side of this equation. And here we have the external applied stress, that is in this case denoted by the yield stress, right? That is what we measure. And we have the Schmidt factor, which is 0.41. And when you divide the critical resolve shear stress by this product of the direction cosines, which is 0.41, we find this normal stress that is needed to initiate a plastic flow within the slip plane having the critical resolve shear stress of 30 megapascals is 73.25 megapascals. So for deformation to occur, the applied stress must be greater than or equal to the yield stress that is found to be 73.25 megapascals. Another example problem. In this case, we have a single crystal of body-centered cubic iron. Remember, iron is or it belongs to a group of materials that have BCC structure, as chromium, for example, oriented such that the tensile stress is applied along 0, 1, 0 direction. In other words, in y direction. Excuse me that the label of this vertical axis is missing. I will correct this typo in the revised version of these slides that are going to be uploaded. So we have a single crystal of FCC where the tensile stress is applied in the y direction, 0, 1, 0 direction. So in part A, we are asked to compute the resolved shear stress along 1, 1, 0 plane and in minus 1, 1, 1 direction when a tensile stress is equal to 52 megapascals. Okay? So here angles are not given. Actually, we don't need the angles, but we need the cosines of these angles, what we refer to as direction cosines. And we know how to calculate the cosines of the angles that are located between two directions. So in this case, the critical directions are the direction of the loading, direction of the slip plane, and direction of the plane normal. All right. So remember, Miller indices of the planes are also denoting the normal directions of the planes. So the direction of the angle phi between the stress direction, applied stress, and the slip plane is given by vector basis vector in the direction of the stress that is denoted by E2. Okay, this is the basis, Cartesian basis vector in the y direction. And this is the E1 plus E2 is the vector that is normal to the plane. All right. So you can identify these E1, E2 directions as I and J directions in your regular notation. Here, I just use E1 and 2 in the place of I and J, and E3 when needed in the place of K. Okay, you might be familiar with the letter notation. Anyways, so the cosine of the angle between two vectors is obtained by the dot product, scalar product of these two vectors divided by the product of the magnitude of these vectors. So E1 plus E2 dot E2 gives us 1 because E1 dot E2 is equal to 0. They are perpendicular in the Cartesian coordinate system, and E2 dot E2 is 1. Length of the normal, which is denoted by E1 plus E2, is equal to square root of t. The length of the E2 is 1. Therefore, cosine of phi is given by 1 over square root of 2, which is, of course, the angle that corresponds to 45 degrees, or in radians, pi over 4. So how about the cosine of the angle that is between the direction of the loading, sigma, which is E2 direction, and the slip direction, which is -1, 1, 1. So -1, 1, 1 can be visualized as or written as mathematically minus E1 plus E2 plus E3. So that product results in 1 because E1 and E2 and E3 and E2 are perpendicular, mutually perpendicular. The only thing that we will survive here is the dot product between E2 and E2, which is 1. And the length of this vector, slip direction, is square root of 3. Length of the E2 is 1. Therefore, cosine lambda is equal to 1 over square root of 3, which corresponds to 0.304 pi in radians, the angle. But we don't need these angles anyways. What we need is just the angle. So the result of shear stress is given by then the external applied stress, sigma, 52, times cosine phi, that is the cosine of the angle between the direction of the loading and the slip plane normal, and the cosine of the angle that is between the direction of the loading and the slip direction. So when you carry out the multiplication, you obtain 21.23 megapascals. So this is the result shear stress. In part B of this question, we are asked to calculate the magnitude of the applied tensile stress that is necessary to initiate the plastic slip. That means if the critical result shear stress is 30 megapascal, calculate the magnitude of the or the amount of the uniaxial stress that is need to be externally applied to initiate a plastic flow. So if it is 30 megapascals, obviously 52 would not generate because 52 generates the result shear stress, which is 21.23. That is calculated in part A, which is smaller than the critical result shear stress. So if you want to calculate the external applied stress that is needed to initiate plastic flow, what you need to do is you need to place in the place of the real, on the left-hand side of this equation, the critical result shear stress, and divide this by product of the direction cosines, in other words, the Schmidt factor. If you do so, there's a typo here. I will correct this also in the revised version of the slides. If you do so, what you obtain is 30 times square root of 2 square root of 3. So these two numbers should appear in the numerator, and this results in 73.48 megapascals. So this is the amount of stress that is needed to initiate the plastic flow if the critical result shear stress is 30 megapascals. So please note that here in this expression, the square root of 2 times square root of 3 should appear in the numerator, not in the denominator. So I will correct in these slides anyways. Okay, so when it comes to polycrystals, as you know from the preceding lectures, are the materials who are formed by combination of different crystal directions or grains of different crystal orientations. So in this picture, you see a nice picture of a polycrystalline material where the grains are nicely depicted, and between the grains we have grain boundaries. All right, and dislocations can move as denoted by these lines. These are the dislocation lines, can move within the crystals, but when they reach to the grain boundaries, they essentially get stuck there because it is difficult for them to move forward in other direction. Within the other grain. So the stronger grain boundaries pin the deformations, in other words, the dislocations, and subplanes in the directions change from one crystal to another one. In other words, one grain to the another one. Therefore, the result shear stress will vary from one grain to the another one. And obviously, when you subject such a polycrystalline material to uniaxial loading, the crystal with the largest result shear stress would yield the first, if you assume that the critical result shear stress is the same for all these crystals, assuming that crystals are of the same kind but different orientations. Others, in other words, the ones that are less favorably oriented, yield later. So metals contain, as you know, generally a huge number of dislocations. This actually makes metals ductile. In the absence of obstacles, grain boundaries or this kind of obstacles, or sometimes dislocations can act as obstacles one another's motion, quite large plastic deformations can occur. But the presence of obstacles, on the other hand, results in hardening in the material, as we will see in the last lab. Sorry, excuse me. Okay. Okay. So this results in high ductility, in other words, capacity of material to deform without breaking, and low yield stress of pure metals. So pure metals are not suitable for that reason, used as a structural material, because generally they are very soft. So instead, what we use is the polycrystalline materials that are tougher and possess higher yield stress. Geometrically, you can consider these three cases. So remember, the condition for dislocation to move is that the result shear stress must be greater than the critical result shear stress, and the critical result shear stress magnitude lies between 0.1 megapascals to 10 megapascals. Crystal orientation can make it easy or hard to move dislocation. As I said in the beginning, if the applied stress is perpendicular or to the parallel to slip direction or slip plane, it would result in a zero Schmidt factor, because one of the angles will be 90 degrees, and therefore in these two cases, the first one and the third one, it would be impossible to generate the plastic flow. In this case, the component of the normal stress in the slip plane, slip direction, excuse me, is zero. Therefore, result shear stress is zero. In this case, on the other hand, area of the slip plane goes to infinity. Therefore, the result shear stress becomes zero, as you see here, because cosine phi, remember, is the ratio of the inclined area to the gross sectional area. So then when it is zero, then the area of the slip plane will become infinity. Therefore, result shear stress will be zero. Energetically, the easiest one will be, or from the mechanism of the slip plane, easiest will be that will generate the highest Schmidt factor will be both angles 45, I guess, right? Okay. That is going to be easier, this configuration, at least in 2D. Tau is maximum at this angle. So this is what we have on a single crystal level, on a single slip system framework, essentially. When you take, on the other hand, a piece of metallic bar and subject to the uniaxial tension, that bar is composed of a polycrystalline microstructure. You generally observe combination of all these mechanisms, and macroscopically measured stress will be your force divided by cross-sectional area, and the macroscopically measured strain will be your horizontal axis. And the combination of these all stresses within all actually grains will be your macroscopically measured stress. So when you consider a stress strain curve of a ductile metal, it is possible to split this diagram into four main parts. The one part is called the elastic region, where the material's response is pretty much limited to the elastic deformations. In other words, when you load the material within this range and unload, you hardly generate permanent deformations or plastic deformations. But there's but there's a point which is referred to as here yield stress, denoted by sigma y. If you deform the material beyond this point, what you do is you start to generate plastic deformations. Okay, and then after the yielding, we have some region where we observe some hardening. In other words, when we deform the material, stress will increase, and there is a region which is referred to as necking region, where the stress starts to soften. In other words, decrease as we deform further. There's another stress value, which is coming before the yield stress, denoted by sigma PL, that is the proportionality limit. So these yield stress and proportionality limit are generally very close to each other, and proportionality limit is still within the elastic region, assumed elastic region, but beyond the proportionality limit, we start to observe some deviation from the proportional linear line, elastic line, and a material behavior will become essentially nonlinear here, as you see. But yield stress is the stress beyond which it's assumed that the plastic deformations are activated, and when you unload at the point beyond this point, you essentially unload elastically. That is the assumption, parallel to this line, and then the amount of strain that you observe here will be permanent strain, will be the plastic strain. Okay. There is one more stress here that is referred to as the ultimate stress. That is the maximum stress that you observe, peak stress observed in the engineering strain diagram. And there's also another point that is the end of the necking region, denoted by F, sigma F. That is a fracture stress. That is the point actually where the bar essentially breaks. And therefore, at this stress, your specimen is not intact anymore, but fractured into two pieces. Okay, this is the typical stress-strain response of a ductile material. So when you take a closer look at these regions, let's first take a look at the elastic region. Sigma y is the stress required to start plastic deformation, macroscopically measured one. It's called the yield stress, okay, as we mentioned. And from sigma y on, plastic deformations start to evolve, okay? So then before the sigma y, before coming to this threshold value, if you unload the material, that will unload elastically without generating any permanent deformation. Stage one is the part that is denoted by yielding, where the behavior is similar to what we refer to as in viscoelasticity creep-like behavior. Stress is pretty much constant, but the strain will develop. It's like material's resistance to deformation is essentially almost zero. So this is very low because only the primary slip systems are active, and these slip systems independently evolve, and dislocations move freely around. Okay, the slip planes are parallel to each other, and only these parallel planes will slip, and they don't interact. In other words, they don't act as obstacles one another's motion. In part two, on the other hand, as you see, this creep-like plateau has ended, and we see some, again, hardening. Other dislocation will start to move along intersecting planes, and therefore we have more dislocations active, and they start to interact. In other words, they form barriers to each other's motion. For that reason, it becomes harder further to deform material. This stage is known as the work hardening stage, and this is actually one mechanisms of hardening the metals, okay, through the deformation. That is based on the accumulation of the dislocations and bringing dislocations in interaction. But the price you will pay is, of course, the reduced ductility. So you can deform the material up to a point here, and then unload and use this material as a as a material that is hardened, because when you load the material again from the fully unloaded state, the yield stress that you will observe will be somewhere here. That is obviously harder than here. But the price you will pay is the reduced ductility, in other words, reduced energy consumption. And that is, in this case, measured under the measured as the area under the stress strain curve. Okay, this is going to be the topic of last lab, I believe, on the uniaxial deformation of plastic deformation of metallic bar. And the last region is region 3. This region starts from the ultimate stress, the peak stress. At this point, plastic deformations start to localize into a neck, and this neck doesn't propagate in contrast to polymeric materials, but localize and reduce in the cross section to a point. And since this is the case, in engineering stress strain diagram, we observe such as softening like behavior, and this process is extremely fast. So in this case, the planes will accelerate sleep, and failure will occur at the end. So this process is extremely fast, and you will observe all these stages of deformation of a ductile metal in lab number 4. Okay, that's pretty much it I like to say about the plasticity of metallic materials. In the upcoming lecture, we will be talking about viscoelasticity. Bye-bye.